Okay, thank you. Okay, so thank you very much. I'm very happy to be here. The first thing I have to say is I will be 60 at the end of the year, so I'm still a young man. So it's a real pleasure to be here, and I'm really lucky, in fact. I have been very lucky. Frédéric talked in his talk about my thesis. I have been very lucky first because a very good advisor, Michel Herman, who gave me asked me to look at the paper of Birkhoff. And this paper of Birkhoff, I think I've never changed really. All my field is related to this paper of Birkhoff. There's something funny is that Michel was really a very, very, very wonderful analyst. And when I began my thesis, I have also to pass an exam, which was called DEA. I have to make a memoir, and he asked me to expose Cam theorem, the version of Cam theorem in the Ziegel-Mother's book. I don't know if you know the proof. There is the constant C1, then C2, then C3, then C4, until C56. And I did the talk with all the constant. And the end says, I think it was a good idea to ask you to do thesis in topology. I'll be lucky to have good students, and I would like to thank Jen and Ginger to be here and to have make a talk. I was very happy to work with them and with all my students. I've been lucky to have very good collaborators. When I began to make mathematics, I was almost alone. In fact, I had no collaborators, but no, I have more and more collaborators, and so I'm lucky to have so many in the rooms. I'm also lucky to have very nice colleagues, and I don't know why it's Frédéric. Here. His job was not easy to expose what I've done, and thanks a lot, Frédéric. When I began, I was young, and in the field there were some people, not so many. There was John Franks, Mike Handel, Shigenori. There were Phil Bowland. In France, there was Albert Faty and Lucien Guillou. And now I see that there is many people who work in dynamics and surface with its topological aspects, and this means that it's really a great pleasure. It's really a field that has exploded, and this is wonderful. And another thing which is wonderful is that the atmosphere of this community. I'm really lucky to work in this community because, as Frédéric tells, it's a very healthy community, very serious in mathematics, but not too serious out of mathematics. Many theorems, but also many beers. And this is really a good thing. I would like also to thank the organizers of this conference. It's the 5th conference in surface dynamics. The first was not official in Pucon, but it's always a good opportunity to meet us. And thanks to Jan, to Piotr, to Gregor, and to I forget. Who is not here? Justina, sorry. Thanks a lot for this marvelous conference. Okay, so I will begin my talk. So this is a new collaborator, but not a whole friend, but a new collaborator with Martin. I will talk, no, I don't need to know it. I will talk about homoclinic orbits for represerving diffeomorphism. So let's see what is the theorem. So here we will consider a closed-oriented surface of genus G, and we put on G an Harry form, and you have an Harry form, you have a measure which is associated, a finite measure, and I will take an integer. R can be infinite. You can think an R to be infinite, and I look at the space of CR diffeomorphisms that preserve omega, and the subspace of diffeomorphisms that preserve omega and that are isotopic to the identity. Okay? I will be interested about fixed and periodic points, but mainly about hyperbolic and saddle points, because we are on conservative system, and saddle points, fixed point, or saddle periodic points. This will be, I will always use this notation. So let's state the theorem. The theorem says the following: there is a residual set in the set of diffeomorphisms, which are isotopic to an entity and preserve omega, such that in this set everybody has a periodic orbit, hyperbolic periodic orbit, and all periodic orbit has a transverse homoclinic intersection. And there is always transverse homoclinic intersection. In particular, this implies that in the set of diffeomorphisms that preserve omega and are isotopic to an entity, the ones that have topological entropy is a dense open set. Okay? It's a dense because you have this, and it's open because if you have an intersection, a homoclinic intersection, you will have it in a neighborhood. Okay, so this is the main theorem. I will say to you what was known. The first thing that was known was the case where R equal to 1. When R is equal to 1, if you work in the C1 topology, you have the C1 closing lemma. And with the C1 closing lemma, you can do a lot of things. There is many properties among, but that include here this kind of things. This is a case where you can use the C1 closing lemma. So the problem is when R is bigger than 1, there is no closing lemma. So we must prove that without this lemma. So what is a good thing is we will almost forget the differentiability. It will be the best way to go to the upper differentiability is to forget the differentiability. So what was known also is a case where G equal to 0 in the sphere. This was due to Robinson for the fixed point and Pixton for the periodic point. And the case of the torus was done by Oliveira. So the missing case was a case where the genus is larger than 1. Okay. Another thing which was known among CR generic properties of diffeomorphism of surface is that the union of stable manifold of periodic points is dense. You don't need to be isotopic to identity in that case. So this was, I did prove it with John Franks in the case of the sphere. And after Jeff Yard gave a proof in the case of any surface, but there was a hole in the proof, and we filled the hole with Andres and Meysam. Okay. But so you know that generic of saddle points, probably a lot of saddle points, but many the unstable and stable manifold are dense, but that doesn't mean that they meet. Okay. The theorem was also, it was announced, it's not published, but there is a preprint at an archive for Hamiltonian diffeomorphism by Jeff Yard. Okay. Hamiltonian diffeomorphism, that means, as Jen explained, then Frederick, that means that your map preserves omega, but the rotation vector of omega is equal to 0. As an element of the homology is equal to 0. I will finish by a result, a very beautiful result of Azaoka Irie, which says that, in fact, generically, there is a density of periodic points for Hamiltonian diffeomorphism. So generically, there is a lot of periodic points. The stable and the stable manifold are dense, or the periodic points are dense. So, but that doesn't say that the stable and stable manifold will intersect. Okay. Okay, so I will just say the following. Where is the... Here. Okay. In fact, Martin came in Paris a little bit more than 1 year ago, and he arrived and said, he drew me something on the blackboard. He recalled me the proof of Robinson. The proof of Robinson, or the important argument of Robinson is the following. You take a saddle point, okay, with a stable manifold, and you suppose that the unstable manifold accumulate on a point here, on the stable manifold. Okay? If you do this, in fact, you can prove that if you push on the left, if you make a small perturbation on the left, you will create a homoclinic point. Okay. It seems easy. But, so, see, why on the sphere it's true, and why, if it is true, there is nothing to prove. But this is true because in the argument, there is a closed curve, and you have to say that this closed curve bounds a disk. In fact, what you are saying is that the homology of the sphere is 0. If the homology of the sphere, if you are on a surface of different genus, you cannot say this. And because you cannot say this, the argument fails. Okay, so Martin said, oh, but maybe we can use transverse foliation, and he told me transverse foliation here, but maybe by using transverse foliation and forcing theory, you can prove something like that. I was a little bit skeptical, in fact, maybe. But we began to look at this, and we forget a little bit the foliation. And we arrive almost at the result, but to finish it, in fact, we need to use transverse foliation. Okay. So I will give, as I say, what is generic. I want to give a little bit more things about what I will call generic. Or maybe here. Okay. The important set will be the following. These conditions are generic in the space of diffeomorphisms. There is no identity here. You see, the set of diffeomorphisms that preserve omega. You suppose that every periodic point is hyperbolic of elliptic, okay, and you suppose that the eigenvalues, the differential of the elliptic fixed point or periodic point, are not root of unity. Okay? There is a condition of on the stable and stable branch. You will ask that intersects transversally. In fact, what you need is the following. If a stable branch intersects an unstable branch, you can have a tangency. It's not forbidden. But if you have a tangency, you also have a transverse intersection. You need that if they intersect, they also intersect transversally. And the last condition was explained by Andres, says that you take an elliptic fixed point, and every time you have an elliptic fixed point, you can surround by branches like this, okay, of a hyperbolic periodic point. Maybe we don't need the properties as explained by Andres, but let's suppose we have these properties. I will say that a map is explicitly generic if it satisfies this condition, okay? So, something important also when you have this property is the following. If you take an element in this set, you can say that the set of saddle points, periodic saddle points, is at least equal to 2G minus 2, or G is a genus. And if F is isotopic to the identity, the set of hyperbolic fixed points is at least equal to 2G minus 2. So why? If you are in this set, you take a fixed point, and you can look at its index, its Lefschetz index. If the point is elliptic, its index is +1. If the point is hyperbolic with no flip, it is -1. If it is hyperbolic with flip, it is 1. Okay? So you know that's -1. So I look at the cardinal of the set of hyperbolic fixed point. I could say, in fact, here the set of hyperbolic fixed point with no flip. I say that is bigger than this because this, when you have such a point, you count by 1, and for the other one, you count minus 1 because you have put minus 1 here. Okay? So this number is bigger than this sum. And this sum, by Lefschetz formula, is nothing but the trace of f star to the n minus 2. Why? But f star is the action of f in the first group of homology. 2, in fact, there is 2. 2 is equal to 1 plus 1. The first one is the action of f in the first group of homology, and the other one is the action of f in the second group of homology, H2. But you have this formula. No, the elliptic points are here. They come for minus 1. I've put minus 1. If you have an elliptic point in this sum, it is minus 1.
Yeah, but the sum is over the rightmost side.
This?
Yeah. This would be the sum of all the indices.
Yes, it's the sum of all the indices. Oh, sorry, there is no. Sorry, there is no h here. You're sorry. Of course, there is no h. Otherwise, it's equality. No, there is no h here. Sorry. Mistake. Okay, there is no h. Of course, you count the elliptic point. This is an important thing. Okay. Something to say is, if there is an elliptic point, you have a strict inequality. Okay, because you will get a minus 1 here. Okay. Or if you have an hyperbolic point with flip. So, well, of course, if f is isotopic to the identity, the action of f star is the identity. So you will get that the set of fixed points, hyperbolic fixed point of f, is larger than 2g minus 2, because 2g is the dimension of the first group of homology. Okay? To get the formula for the periodic point, you have to look a little bit more. This is nothing but the sum of the power to the n of the eigenvalues. Okay? The eigenvalues can be real or complex, but you can suppose, by taking an n sufficiently big, that all the arguments are very close to 0. All the arguments who have the eigenvalues are very close to 0. So, if there exists an eigenvalue that is bigger than 1, this will be very, very big. And so you will have infinitely many hyperbolic periodic points. The bad case will be that if all the eigenvalues are modulus 1. Okay? In that case, that means that you can find n such that this is very close to 2g. But it is an integer. So it is 2g. Okay? So you can find an n such that it is equal to 2g. And so you get the formula.
Because the eigenvalues are almost 1.
They are almost 1 by your power. So the sum is almost 2g. Okay, so this will be important in the future. So let's see. Okay, so I will give the precise statement of the theorem. There is 2 parts in the theorem. The first part is the following. If you take an element in GR, okay, and if you are 1 fixed point more than the minimal, every periodic hyperbolic point has transverse intersection. If there is more than 2g minus 2, all have this property. And here the map does not need to be isotopic to the identity. Okay? And the second theorem says you that if you have a map, a diffeomorphism which is isotopic to the identity, you can perturb it such that you have more than the minimum. For example, if you are in the torus, it says you that you can perturb a map in such a way that you have at least 1 periodic point. And the way you do this is the following. You take a diffeomorphism that preserves omega, of course, and which is isotopic to the identity, and you compose with a small rotation such that the rotation number becomes a rational number. And if it is a rational number, you can use Conley-Zander theorem, that Frederick explained us, that says that you have a periodic orbit. So you can create a periodic orbit on a torus just by composing by a small rotation. You cannot do that on the surface of genus G, but you can do something similar. And this will be the second part. So if you have this, of course, you take a map F, you perturb it such that you have more than this number, and after you approximate it by an element of GR, and you win. Okay? So these are two different theorems. I will try to give you the proof of the theorem A, and I will try to give you an idea of the proof of the theorem B. The methods are different. One is related to works with Andres and Messam, and the other one related to work with Fabio. But they share something in common. They all use the notion of homology. Homology will be fundamental in the proof. So let's do some comments. Oh, and first comment. There is also a class of isotopy such where you have periodic orbits. Suppose, for example, that F, you can look at F and look at its Nielsen-Thurston decomposition. If there is a pseudo-Anosov component, in that case, you have infinitely many periodic points. So you can use theorem A. Okay? So the reason I put identity... What?
He's happy.
Ah, you're happy? No, but I think we think, as Martin, that we don't need to make a perturbation result if you're not isotopic to identity. Our big problem was looking at the Duane twist around a simple closed curve which is not homologous to zero. But maybe it works. We have an idea to make it work. But probably the result is true. Probably what is true is that the map is not isotopic to identity. You can apply theorem A directly. But this must be proven. Okay, so some comments. A nice comment is the following. If you take a map F, which is in GR, explicitly generic, and if there is a point with transverse homoclinic intersection, then every point has a property. Because if there is a point with transverse homoclinic intersection, there is infinitely many periodic points. And so you can apply theorem A. Every point has. So if somewhere there is one which has homoclinic intersection, for everywhere there will be the property. Another thing is the following. If F is explicitly generic and is Hamiltonian, in that case, we are more fixed point than the minimum number. It can be proved that you have at least 2G plus 2 fixed point and at least 2G which are hyperbolic. But 2G is bigger than 2G minus 2, so we win in that case. So we get the Hamiltonian case because of that. Of course, something which is important, if there exist elements which have exactly 2G minus 2. So you need a perturbation result to prove the result. Andres showed me the example is in the paper of Shah. I didn't believe to it, and Andres, look at this, at this figure. In fact, you can find translation flows if you can define it by translation flows. Such example exists. So in the case isotopic to identity, you need to perturb. It's not sufficient to be in GR. Okay, it's not sufficient. Okay, so I will begin the proof of theorem A. Something which is important is the notion of regular open set. A regular open set of a surface, we have a surface, it's a connect open set of finite type such that the impression of every none is not reduced to. So I will draw you this. And then, so this is the surface. This is the ugly thing. If you look at V, this is a regular open set. if I take a if I take in this example, you have 3 hands. No, this is not well. Bon. You have an hand here, you have an hand here, and you have an hand here. You have 3 hands. And the impression is not reduced to a point. The impression is the limit, the set of limit points. If I put a point and take the complement, it's no more regular. I don't want that the connect component of the complement has fixed point. An example is if you take a non-trivial continuum in the surface, every connected component of the complement is regular. Okay. Okay, so there is 3 natural compactification of this set, the closure of V that you see in the figure, the N compactification. In this example, the N compactification is something like this. It's a 1 torus, it's a 2 torus, because you have put an N here, and an N here. This is a compactification by end. And there is a prime N compactification, where you consider the prime N compactification here. So in that case, well, it's a complement of the 3 disk. You have blew up every end and adding the circle of prime ends. Okay, and Andres explain us how it was constructed. Okay, and this I will call V prime. So this is a surface with no boundary, and this is a surface with boundary.
So the wiggly ends are not separating the surface?
The ugly ends? No? No, it's connect. V is connect. V is this place. Okay, I suppose V is connected. Okay? So, yes, I say that a regular open set is a finite type. Finite type means there is finitely many ends. Okay, there is finitely many ends. Okay, so you take this and you have the 2 following results, which we are already stated by Andres. The first one is a result of John Mather, which says that if F, you suppose that F is in GR, is explicitly generic. In that case, there is no periodic. So if you take, I suppose, oh, I forget to, it's fixed. V is fixed by an element of F. So in fact, what happened is, what is important, the Prime theory, is that it's that, of course, you can extend your map F to the N compactification. You will get periodic points. But what is important with the Prime theory, that you can also extend the restriction of F to V to the prime N compactification. And in that case, you get periodic circles. Taking a power, you can suppose that they are fixed. And the result of Mather is there is no periodic point on the prime boundary. Okay? So when you do that, you have no periodic point. What does it mean? It means that on the N compactification, the index of this point is 1. Because that means the rotation number, if it's fixed, is irrational. So for every power, the index will be 1. So in a certain sense, that means that these points are elliptic points. They share the same properties as elliptic points. The second result with Andres and Messam, which says that here also there is no periodic point on the boundary. There is no periodic point on the natural boundary. Okay? So this will be useful to prove the following. We never know what will happen. Oh, consequence. The first consequence is a classical consequence of Mather, which says that if F is explicitly generic, the 4 branch of every hyperbolic point accumulate on the point and have the same closure in this. They have the same closure. The second result is a consequence of the second theorem. It says that if you have two periodic points, hyperbolic, and the closure are different, they are not the same closure, then it's because there is no periodic point, the boundary, then the point Z prime is not in key Z, in the closure of Z. And if it's not in the closure of Z, its four branches are not also are disjoint from the closure of Z. Okay? It's possible that KZ and KZ prime intersect, but they don't intersect on the branches. It's possible that they intersect. I don't say that they don't intersect. Okay? So this is a very important property. So, now I can define a relation of equivalence between hyperbolic periodic points saying that Z is equivalent to Z prime if K of Z is equal to K of Z prime. Okay? If they have the same closure of the branch have the same closure. K, I didn't. KZ is the same closure, KZ, is the closure of the branches. The four branches have the same closure. It's okay? When you take an hyperbolic point like this, and you take the closure, you get a continuum, an invariant continuum, and this is a closure of this set. Okay, so you get.
So do we know already that they have homoclinic intersections?
No, I don't know. All these things are things which are in what was known. Okay? No, they accumulate, but they don't have intersection. It's true in the case of the sphere. And this is a Robinson argument, in fact. In fact, it's Pixton argument. Because there is homology, it's not true.
So the two are equivalent if they have the same K?
Yes, they are equivalent if they have the same K. To every periodic point is associated a certain compact or periodic compact set.
What is this sigma and equivalent? Oh,
Say
class is homoclinic, I see.
an equivalent class. You call kappa the equivalent class, and you say that it's homoclinic if every point in this class has homoclinic intersection. It's easy to prove that if there is one that has homoclinic intersection, all have homoclinic intersection. Because you will, if you have homoclinic intersection, you will have something like that. But you know that your other periodic point, the stable manifold will arrive in a neighborhood, so it will have to cross a stable one. So you have two types of classes.
You don't have to say transverse.
No, but I have supposed that it's transverse, so it's better to suppose this. Okay, so I will need the transversality after, so I suppose at the beginning that there is transversality. So that's the case, there is no problem. Okay, so you see, you have divided your set of periodic hyperbolic points in classes, and you want to prove that each class is homoclinic. Okay, so what is the surprise? It's always a surprise. So the theorem K. No, they are not disjoint. They are not disjoint. But a point which is not equivalent is not in the set. But its closure can intersect the closure, but it does not intersect on the branch. You see?
So that they cannot be nested, for instance.
Oh, yes, it will be nested.
Nested, no.
Nested? No, nested. What you? No. They cannot be nested. They cannot be nested. No. Because otherwise, the smallest one will be in the. No. We really have this situation. You must imagine, for example, you have an invariant curve. Suppose it's minimal from. You have an hyperbolic periodic point, and the closure contains the circle. And from the other side, you have another hyperbolic point, such as the closure intersects the circle. So the intersection will be exactly the circle. This is possible. Okay? Okay, so the theorem Ka will be decomposed in three theorems, A1, A2, A3. A1 says you something, So the weaker theorem, so with the stronger hypothesis, is this one. If you suppose that there is no 2g minus 1, but at least 2g, which is bigger than 2g minus 1, periodic point, in that case, there exists a periodic point with transverse intersection. Okay? The theorem B, A2, no, not B, A2, we say you that you have the same conclusion if you have the hypothesis which is weaker, and the theorem A3 is nothing but the theorem. With a weaker hypothesis, we have a strong conclusion. So we start with a strong hypothesis, weak conclusion, weak hypothesis, strong conclusion, a weak hypothesis, okay, weak hypothesis, strong conclusion. We're getting better, all this theorem better and better. Okay, let's go to the A1, which is probably the most, the fundamental thing, where you are really see homology. Okay, I say the following. There exist, as you will see, the result is algebraic. We will do algebra. I suppose that there exist more than 2g hyperbolic periodic points. Okay, so I can divide them in classes. I've defined the notion of classes. Of course, we always on G here. I say I take a point Zi, and for every Zi, I can find a disk Di, which is a free disk. And if I take another one here, no, D E prime, all they are free disk. Oh, not like this. And the condition is the following. The disk, if Zi is equivalent to Zi prime, they are the same disk. We associate the same disk. If two, it's here. You say, you associate 2 points which are equivalent, the same disk. And 2 points which are not equivalent, 2 disjoint disks, such that in fact, you really have this figure. Okay, so you have a certain number of disks, the Di. Their image, the family of images are completely disjoint from the disk. So why you can do this? It's because it's very easy. You take a point, for example, you fix a point of the stable manifold of Zi. Okay? You know that this point, which is a stable manifold of Di, is not in the closure of the branches of Zi prime if Zi prime is not equivalent to Zi. Okay, so I can find a small disk that is disjoint from the stable manifold of the other points. But the points Zi prime that are equivalent to Zi, the branches arrive here. Okay, so you see what I do? So I choose a family like this. And there is no problem to do this. If all the points are equivalent, I have a unique disk. If none of them are equivalent, I have 2G, the number of disks, the same number of disks. But you can have mixtures. This is purely, there is nothing to, very easy to say. And now what I do is the following. I construct a loop in the following way. I take this point, and I take the unstable manifold, and I know that all the branches will arrive in Di. So I take the first point, I arrive in Di. And, okay? And I call this, I call this alpha E U.
Di contains a point in the stable manifold of Di.
There is no stable manifold here. It's an unstable manifold. I take the unstable branch, two unstable branch.
And then you take some point in there.
This branch have to meet this disk.
The closure of the other is the same, so it has to end.
Exactly. And after I close as I want like this. This is not important. Okay. What is important is this curve does not mean f of Di because I am on the unstable manifold. So you will meet first this disk before meeting this disk. Okay? And you do the same here. And you do after the same with the disk, with a stable manifold. But with a stable manifold, first you meet f of the I before meeting the I, and you close. And you close, okay? You have constructed such a way a lot of this. We are not on. We are on the surface. I do agree. I am authorized to do this. Okay. If I'm on a sphere, I cannot do this, but this means that there is intersection. I give you a proof that there is homoclinic intersection in the case of the sphere if you are in GR, because you have a disk and you see that this disk, this curve and this curve has an intersection number which is 1. If there is no, what is important is when you have a family of loops, and when you take a stable loop and an unstable loop, they intersect on the stable branch and the unstable branch. Because the other ones, they don't count the beta. You see? This is an important point in the proof. If you have seen this.
So what are lambda?
Lambda is a loop. Alpha is a portion which is on the manifold, the stable and unstable manifold, and beta is a small thing which is inside the disk. Okay? This is a very important point of the proof. You have a family of this like this. Hmm? D is in the DI, so it never intersect alpha because no, the only possibility are if somebody intersects, they intersect. I have no.
You close the loop with an arc in the I.
Yes.
And you make a stable one with a stable.
What is important is a stable loop will never meet di or di prime. An unstable loop will never meet f of di and f of di prime. This is the important point. We really have a nice drawing. Okay? I can go to the... This.
They will not meet if they are not equivalent.
Yes, if they are not equivalent, it doesn't meet, clearly. But we have something more precise. I told you I will work in homology, so I work in homology in coefficient in Z2, because there is only 0, 1, 1, which will be simpler. And I consider the class of a loop. I say the following: if I and I prime is different from I prime, and if the intersection is empty, then the link, this is the intersection. You have an intersection form in homology. And it means it's the algebraic intersection of loops. In that case, 0, 1. It's 0, there is no choice. Of course, because of this. So if this does not meet, this is empty, and so this is empty. Okay? But if the stable manifold of the I and the unstable manifold of the I intersect only on the I, that means there is no homoclinic intersection, the same result tells you that you have 1. Okay? You see, this is 1, the intersection of the stable and the unstable is 1, if there is no intersection except at the point Zy, and the intersection is 0. So you have exactly this. And so this is the proof. I consider the family of the stable loops. It is linearly dependent because you have more than 2G loops, and the dimension is 2G. So I can suppose that E is minimal from this property. Which is important is that the family is linearly dependent. So I take a subfamily which is linearly dependent and minimal. So I suppose that it's I has this property, will be simpler. That means that every lambda IS is a linear combination of the other ones. Okay? Because it's minimal. And so, suppose, for example, that there is no homoclinic intersection. W the I intersect Ws of the I is equal to the I. The intersection number is 1. But this one is a linear combination of the other one. So there is another one such as intersection is 1, which means that there is one stable manifold of the I meets a stable manifold of the I prime. I know my hypothesis, you have transverse intersection. And now you use the inclination lemma. You will have a cycle of intersection. Okay? And so you have a homoclinic intersection. Okay? So it's really algebra, just this algebraic level. In fact, it was really to, this argument in the case of sphere was quite known, and it was just to try how to generalize it in higher genus. So this theorem A1, we have supposed that there is more than 2G. And you want to know, and you will find that there exists a point with a homoclinic intersection. So now we want theorem A2. We suppose now.
I'm sorry, why, if you had only more than 2G minus 1, the last theorem doesn't work?
Because the dimension of the homology is 2G. So you must, you must be larger than 2G. Yeah. Okay? But at least this is the interesting thing. If you are bigger than 2G minus 2, you want to see that the same thing. So I can suppose that G equal to 1, because if G equal to 0, if it's on the sphere, 2G minus 2 is equal to minus 2, and 2G is equal to 0. So it's the same property to be bigger than 2G minus 2 and to be bigger than 2G if you suppose that you're also positive. So the case where G equal to 0, you have nothing to do. So you suppose that G is at least equal to 1. So you can take a cyclic cover of your surface S. You start with the surface S. For example, we are in this surface, and we suppose that we have more than 2 points. So we have 3 points here. Okay? 2G minus 2 is equal here. G equal to 2. 2G minus 2 is equal to 2. So you suppose that you have at least 3 fixed points. So let's suppose that we have 3 fixed points. You just cut here, you take a curve like this, and you take a cover like this. And what you need is really a 3 cover. Up. I think I forget something. Ah, here there is another one. Okay. I pass, I cut and copy 3 properties. So you have, how many points you have here? You have 9 points. Okay? In my figure, you have 9 points. And what is the genus? The G prime is equal to 4. So 2G prime is equal to 8. And 9 is larger than 8. Okay? So what I do is the following. I take this cover, and I use Hall's theorem, Marshall-Hall's theorem, which says that if you have a homeomorphism of the surface and a finite covering, you can always find a polar of the map F that can be left. The reason is that there exists finitely many subgroups of a given index in the fundamental group of S, because the fundamental group is finitely generated. Okay? So F acts naturally on the set of subgroups of index M. And there is, as it's a permutation, you can find M that it fixes. Okay? Every subgroup. So if it's every subgroup, you can use the lifting theorem, and you know that you can lift F to a map F prime. But F prime is in GR. It's easy to see that everything is still true here. And you have more. In fact, what happened is that the genus increases less quickly than the number of periodic points. And so you get that for a certain finite lift, you have more than 2 G prime points. Okay?
This is magic.
It's a little bit magic, yeah. Okay. So, you have to prove the other one, which will be maybe more magic. We have to suppose now that every point, so I want to prove that there is every point has transverse intersection. So, of course, I can suppose that there exists at least 2 classes. Because if there is a unique classes, if I know that one of the classes is homoclinic, so it's finished. Okay? So there exist at least 2 classes. So this implies that every class is included in a periodic regular open set. Why? You have Z prime. Suppose that Z is not in kappa. You take you take K of Z, which is a compact continuum, invariant or periodic continuum, and you look at the connect component that contains the other one. It is regular because it's a connect component of a non-trivial continuum. It is regular. Of course, it's not nothing. So every class is included in a periodic regular open set. Okay? Okay, so if I take your periodic, so this is a, I will probably make a bad drawing. Okay, this is V, for example, and I know my point Z, so I take a class, Z is in kappa, and I know it's in V. So, of course, V is periodic. I take a power that fix V, and I look at the N compactification. I told you that the N compactification, these points are like elliptic points. So what does it mean? It means that the set of periodic hyperbolic points that are in V, or V here, the same, there is more than 2G minus 1. The same proof tell you that in V prime, in V, there exists an homoclinic, a class with a monoclinic intersection. Okay, another one, because the other one has disappeared because we have taken a complement of K of Z. Okay, so we have another one. If you do this, you see that there's infinitely many classes with homoclinic intersection. But this is not the result we want. We want to prove that every class, okay, has this property. It may happen that there is infinitely many classes. But the other magic thing is, if you suppose, you can always suppose that there exists no periodic regular open set of genus strictly smaller than G prime containing kappa. You know that there is a regular open set that contains kappa. But you can define the minimum genus of all possible regular open sets that contain kappa. And if it's minimal, in that case, you can prove that there exists that kappa has more than 2G prime minus 2 points. And in that case, you will prove that kappa is homoclinic. So what's the reason? The reason also is magic because, so you have a lot of hyperbolic points, but what will be magic if you can gather them in blocks such that they will become elliptic fixed points, periodic points. The reason is following. I suppose that V has this property. You see, when I look at the chi of Z, okay, this is chi of Z. What is important is, so you know that in V there exist classes which are homoclinic. But they will be, so you have some hyperbolic points which are not in kappa of Z. But the fact that you cannot, that the genus is minimal, said you that all the connected components of the complementaire of K prime are disks. They are disks. They don't have topology. Otherwise, you could find another, you could decrease, you can decrease the genus of V. The fact that G is minimal tells you that all they are complete in disk. But what is a disk? If you take a disk, here on the boundary, you can apply the result to say you that the boundary is an irrational number. It's irrational. It's periodic, and the boundary is a rational number. So you can replace all these families of hyperbolic periodic points by an elliptic periodic point. Of course, there is elliptic periodic point inside, but and so it's finished. Okay. So I have not. How many times is it? 3 minutes. 3 minutes. So in 3 minutes, I will say you. I don't have the time, so I will go by. You know what happened? You know that you suppose you have isotopy to identity, and you want to prove that you can find perturb such that you get periodic points, more than 2G minus 2 periodic points. If it's a proof by contradiction. If it's not possible, there exists an open set of diffeomorphism, which is in GR, which is really in GR, such that all these points, they are exactly 2G minus 2 fixed points. They are like translation flows. That means you have really an open family of maps which is really like a translation flow. They all have a lot, they are exactly 2G minus 2 fixed point. And you know, the stable and stable manifold, you can prove they are dense. And you can prove also the map is transitive. Otherwise, it's exactly the same stuff. You can put somebody in, you will find regular open set, and it will work. So you really have a family of maps, and so you really have, for each of them, you have a stable manifold, and stable manifold, you want to make a perturbation such as a cross. But you imagine that it will be not possible. You make a lot of perturbation, so they will move, but they will all move without crossing. It's impossible. It's impossible.